Chapter 6, Part 6, Factors Affecting the Rates of SN1 and SN2 Reactions, this time focusing on the identity of the leaving group and solvent effects. First, we'll discuss leaving group identity. Remember, in a nucleophilic substitution reaction, the leaving group leaves and takes the electron pair that bonded them to the substrate with them. The best leaving groups become relatively stable anions or neutral molecules when they depart, or in other words, they are weak bases. The stronger the conjugate acid of the leaving group, the better the leaving group. So, for example, good leaving groups include iodide, bromide, chloride. These are all conjugate bases of strong halogen acids. Water is a great leaving group. It is the conjugate base of hydronium. And all of these are significantly better, which is what's meant by these multiple arrows here, than fluoride. Fluoride is the conjugate base of hydrofluoric acid, which is a weaker acid. Bad leaving groups include hydroxide, carbanions, and hydride. All three of these species are very strong bases, which means they are highly reactive. They're not going to be very stable. They're looking for a proton or other Lewis acid to bond with. So if you perform a reaction and you form hydroxide or a carbanion or hydride, you've just created a much more reactive species, and that reaction is unlikely to move in that direction. Strong bases tend to be much better as nucleophiles than as leaving groups. So let's talk about why. A leaving group has to be able to stabilize the transition state. So for example, in an SN1 reaction, as that bond between the electrophilic carbon and the leaving group weakens, we end up with increasing positive character on the carbon and increasing negative character on the leaving group. By the time the bond is fully broken, you have a carbocation and you have this leaving group that has a negative charge on it, or maybe perhaps became neutral. In order for this to occur, especially in a situation where the bond breakage is occurring without an attacking nucleophile, this species has to be very stable on its own in order for this reaction to move into this direction. And the leaving group must be able to stabilize whatever charge you may have created. For an SN2 reaction, the leaving group is going to be developing negative character as the nucleophile is losing negative character and forming the bond here. And the leaving group needs to be able to stabilize that. So weak bases are going to be more stable and better leaving groups. Let's look at how solvent affects the outcome of these reactions. I do want to say something about solvent before we go into the different types of solvents. Solvent is one of the last factors that you'll look at in a reaction. It's not going to help you decide whether a reaction will occur as SN1 or SN2. Instead, what it can do is be a useful tool in the lab if you're running an SN2 reaction and you need to speed it up or guarantee that it's going to occur at all. Choosing the right solvent can help make that happen. So for example, we have two different types of solvents that we use here. So you have polar aprotic, which is going to favor SN2 reactions. This includes acetone, DMF, which is dimethyl formamide, and DMSO, dimethyl sulfoxide. All of these reactions are polar, all of these solvents are polar, and none of them have hydrogen atoms that are going to be capable of hydrogen bonding. They are, however, capable of dipole-dipole or ion-dipole interactions. They will be able to solvate positive ions. So for example, if you put sodium iodide in acetone, the sodium and the iodide are going to separate. And in an SN2 reaction, what we want is for the iodide to be free to act as the nucleophile. And since the rate of the SN2 reaction does depend on the concentration of iodide, we want that concentration of iodide to increase rapidly. So if you're in acetone, the acetone molecules, being polar, can have dipole ion interactions with the sodium plus ion, and this allows the sodium and the iodide to separate, increasing the concentration of iodide while occupying the sodium. An unhindered nucleophile can increase the rate of reaction up to 1,000,000-fold, so this is a significant effect. Another factor is in the polar protic solvents. Polar protic favors SN1 reactions. So these polar protic solvents are polar and have at least one hydrogen atom capable of hydrogen bonding. So for example, water and alcohols. These solvents will hydrogen bond with the leaving group, allowing the carbocation to form more easily and faster. So for example, in this reaction, what we want is for the chloride to be able to leave with those electrons. And the hydrogen bonds that the chloride is able to form with the water molecules will allow the chloride to separate more easily. This is going to lower the energy of that transition state where this bond is weakening and the negative charge is beginning to develop on the chloride. And then finally, once the chloride is separated from the carbons, you have your carbocation. And then your chloride anion is occupied by hydrogen bonds with water, the same way that we saw the sodium on the previous slide being occupied by acetone. There can be some negative effects from solvents. If you have protic solvents in an SN2 reaction, you can hinder the nucleophile by hydrogen bonding with the nucleophile. So think of that example with sodium iodide and acetone. If instead we had sodium iodide and water, the water would interact with the iodide when what we actually need is for the iodide to be very free to participate in the SN2 reaction. The more weakly solvated an ion is, it will be a stronger nucleophile. So if you use a protic solvent in an SN2 reaction, this can actually reverse our usual expected nucleophile trend. So in an aprotic solvent, and also in general, fluorine is typically a better nucleophile than chlorine, and then greater than bromine, greater than iodine. But in a protic solvent, fluoride is going to interact much more strongly with the hydrogen atoms of water. It would be much more strongly solvated, and so it actually flip-flops our expected nucleophile trend.